Welcome back, everyone. So I am super excited about this lecture. This is a new one. I haven't given this before in class, but I've been meaning to for a long time. And it's all about the wave equation, which is one of the most important partial differential equations in all of physics. It is everywhere. And so I like to think about kind of motivating the wave equation by thinking about music and acoustics. So a guitar or a vibrating guitar string is a really, really good example of a wave equation that we're going to derive and analyze and solve. So this is a two-part lecture, and in the first lecture I'm going to motivate, what is the wave equation, where does it come from, what are some examples. Like literally these examples are everywhere, from acoustics to optics, you name it, it's everywhere. And we're going to derive this wave equation from scratch, from first principles physics, and then tie it back to some intuitive examples like a vibrating guitar string. So we're going to ask questions like, why does tensioning the guitar string, making it more tension, make it a higher pitch sound versus a lower pitch sound? Things like that. Why are the thinner guitar strings higher than the thicker guitar strings? Why does changing the material from, let's say, steel to nylon change things? That's all kind of an outfall of the wave equation. So I'm going to come back to this in a little bit. And for right now, I'm going to start by kind of deriving and explaining what I mean by the wave equation. Good. So maybe I'll use some colors here. So the idea of this wave equation is that you have, I'm just going to write down the equation, UTT equals c squared uxx, where u is going to be the height of some string. So we're going to assume that we have a string that is pinned, let's say, between two locations. So this is going to be the x equals 0 location, and this is going to be the x equals L location. So that's the length of my guitar string in this case. And what we're assuming, there is some like rest position where the string is just under some tension, but it's not moving. And we're defining u to be the height or the displacement of this guitar string from that rest position. So these are all my u of x and t. Okay, so the displacement of that string is a function of its position spatially along the length of that string, and it also changes in time. You can picture this thing literally, kind of oscillating. The guitar string is oscillating, and that's what's creating these acoustic waves. So that's one example of the wave equation, is something like a vibrating string. This is where the boundary conditions are pinned so that both the x equals 0 and x equals L boundaries are pinned to be 0 displacement. I think it's actually really interesting that the acoustic waves that this vibrating string generates, these acoustic waves that you're hearing from me talking or from that guitar string vibrating, those also satisfy this linear wave equation. So even though acoustic waves are pressure waves traveling through a fluid medium, and we know fluids are governed by the nonlinear Navier-Stokes equations, acoustic waves are kind of infinitesimal shock waves, if you like. They're traveling at the speed of sound in the medium, whether it's air or water or helium. And those pressure waves, those shock waves, are infinitesimal, so that they don't create any kind of noticeable change in entropy as they travel, which is why acoustic waves travel such great distances. That's why you can hear an airplane flying overhead from great distances, things like that. Okay, I should mention that this c here is the wave speed, so maybe I'll just make note of that. So c equals, let's say, the wave speed. And if we're talking about acoustic waves, this would be the speed of sound in the fluid medium. If we're talking about optics, this would be the speed of light in a given medium. So that's another example, is optics. Okay, so if I have, let's say this is my eye, and I have light coming in, from some source and bending through the optics of my eye to hit my retina. These plane waves from Maxwell's equations, from electromagnetism, those are also governed by the linear second order wave equation, okay? Where, you know, the second derivative of this fluctuation, whatever that fluctuating quantity is in time, is equal to the wave speed squared times its fluctuations, the second derivative of those fluctuations in space. So optics, acoustics, vibrating strings, all of these are governed by the wave equation. I had the guitar string, which is pinned in two places. But if you also have something like, let's say I have, I think every kid has done this when they were, you know, young. You take a rope and you flick the rope and you send a traveling wave down that rope. So maybe it goes in this direction. In that case, the boundary conditions are a little bit different than the guitar string. So now one of my boundary conditions, my hand is forcing it at some profile in time. And then the other boundary condition, if it's a very, very long rope, you would assume is kind of you know, unpinned or free. And so you get different solutions to those wave equations, but they're still governed by the same physics, whether depending on the boundary conditions. What are some other examples? Some of you like to slackline, I'm pretty sure. And so if you take a tree, let's say you have a cool tree and you have your slackline set up around this tree, and you are a human on this slackline. And so if you're anything like me, you're probably vibrating a little bit. And then also the string, the kind of the cable that's connecting. There's another tree over here that's connected to the other side. This cable is also vibrating at some frequency. And so we're going to be able to understand, so we're going to derive this wave equation. We're going to see how this speed of the wave speed, at least in the guitar string and this slack line, depend on things like the tension in the rope or the tension in the string, the thickness or material properties of that string. Those are all going to kind of go into this wave speed C. But these are just some of the many, many, many examples of how the wave equation comes up in physics and in engineering. I guess, you know, I also think about if you throw a rock in a pond, you're going to get, you know, some kind of ripple effect in that pond. You know, that's also going to travel according to this wave equation with some assumptions and simplifications. Okay, good. So I'm going to start deriving this wave equation. I'm going to specifically derive it for this kind of guitar string because that for me is very intuitive. And then we're going to analyze the properties of this equation and understand how kind of the physics and the math tie together. So something I like to also point out is a little bit of the history of this wave equation. So this wave equation in 1D as a partial differential equation was written down by D'Alembert, I think in 1746. This was not the first time that a vibrating string was mathematically considered. That was done earlier by Brooke Taylor. Okay, so that was, you know, a decent bit earlier. Kind of right after Newton's F equals ma, Brooke Taylor started analyzing vibrating strings. But the partial differential equation was written down by D'Alembert in 1746. And then about 10 years later, Euler generalized this to a full three-dimensional wave equation. So in 2D, you can think of the membrane of a drum as a two-dimensional wave equation. In 3 dimensions, Euler generalized this. So that would be like acoustic waves in 3 space traveling in all directions. And I guess in that case, this uxx would be replaced by a Laplacian of u operator, okay, which we've seen before in our other examples of partial differential equations. Good, okay. So I think I'm going to jump into this thing. So this is the definition of what I mean by my variable u. It is the height of my guitar string. It could also be the kind of amplitude of my pressure, you know, wave if I'm talking about acoustics. There's different, you know, meanings of u in all of these different physical scenarios, but for here I'm going to zoom in on this guitar string and just think about that. And so what we're going to do is try to derive this equation here from scratch. And so what I like to think about is, at the end of the day, the wave equation is actually one of the simplest equations to derive in physics, because it really is just F equals ma. It is the conservation of momentum in this kind of elastic, springy medium. Now, this is kind of a meaningful lecture for me, because it actually took me a really long time in my mathematical career to feel comfortable and confident kind of deriving and analyzing the wave equation from scratch. So, I loved calculus and differential equations when I was a kid, and I remember saving up my money when I was, a teenager to buy this differential equations book. It was the one differential equations book that Barnes & Noble sold. It was a really, really good book. And I remember working through kind of the ordinary differential equations, and I got to the section on partial differential equations, and it started with the wave equation. And the derivation of the wave equation always confused me, and I just got stuck time and time again, on 2 pages in to this section on partial differential equations. And eventually I just kind of left it and didn't really revisit partial differential equations until I was a grad student. And so years later, now that I'm teaching this material, I think it's really important, to be able to derive these things from scratch, to really physically understand how they're tied to simple concepts like F equals ma and conservation. And I just kind of want to demystify how this is derived and analyzed, because for me, this was kind of a mental block. And I'm telling you this because, a lot of you see me derive these things and it looks easy, and you don't maybe know that this took, in this case, decades for me to really feel comfortable with this derivation, and also with kind of all of the physical interpretations and how to really kind of manipulate this equation and understand how it relates to things like a guitar string or a slack line and things like that. Good. So F equals ma, and what we're going to do is we're going to zoom in on a little teeny tiny section. We're going to look at a little section from x to x plus delta x. So I'm just going to draw kind of a little picture over here where we have some section of this, and I hope I've given myself enough space here, from x to x plus delta x. And this is a tiny little infinitesimal section of my guitar string, and we're literally going to compute the forces, the masses, and the acceleration on this little section of string that's vibrating. We're going to make some assumptions about what can be happening, and then we're going to derive things. So what are the basic assumptions here? The basic assumptions, at least a couple of the basic assumptions, are that we're going to assume that gravity is negligible, or gravity is negligible compared to the tension in the string. Gravity is negligible, don't know how to spell, negligible, really compared to tension in the string, to string tension. Good. Which means we're going to, tighten this guitar string up so that when it's vibrating, the vibration is really only determined, the motion is only going to be, these forces are only from that string tension, and gravity is really negligible. And you can kind of convince yourself that this is true, because if you play guitar in kind of the normal upright position, it doesn't matter if you play it this way, or if you play it this way, or if you play it, if you rotate it in any plane, it's going to sound about the same, because gravity has a negligible effect on that guitar string. What are some other assumptions? Some other assumptions we're going to make are that the deflections, even though I've drawn a really big, kind of cartoonishly large deflection, we're going to assume that all of our deflections are small. Okay, so deflections are kind of small. And this is going to allow us to make a small angle approximation. So we're going to assume that all of the kind of angles throughout this path are small. And it's going to allow us to make a very, very important third assumption, which is pretty much related, which is that the tension in this string is constant throughout the string. We have basically the same tension everywhere in the string. That's kind of how tension works for small deflections. So tension is the same throughout x. Okay, so at every x location, I'm going to assume that the tension in the string is the same. And so this is an important variable to mention, is that the tension, we're going to call this T, and this is a force. Okay, so tension is literally a force in that string. So there is a tension vector here, T, and there is a tension vector here, T, and those are the same forces. They have the same kind of force T at the left side of the segment and at the right side of the segment. And essentially what we're going to say is that because, again, I drew this so that it's not really a small angle, that's just for visual, to make it visually easy to see. But what we're going to assume is that these are small angles, and so the kind of x component are approximately equal, because cosine of those small angles are about equal to 1. And so there's not going to be any horizontal motion of the segment. There's only going to be a vertical motion because of the vertical components of these two tensions being different and causing an acceleration. So that's where the force is going to come from, is from the vertical component of these two tensions at the left and the right part of my segment. And the mass and the acceleration I'm going to write down right now. So the mass in this little segment, we're going to say is equal to rho delta x, where rho is essentially the density, or let's say the mass per unit length. So this is called the linear density, which is the mass per length. And so this is, already we're going to start seeing that, a thicker guitar string on the lower, for example, E string, is going to have a larger linear density. It's going to have more mass per length than the really small, kind of higher E string, which has a lower mass per length. So that's presumably going to change kind of the wave speed and the sound that those strings make. Okay, so this is kind of all that we need to start building this solution now. So literally mass is rho times delta x. And so mass times acceleration, ma, is just going to equal rho delta x. And in this case, acceleration we're only talking about acceleration in the vertical direction, because that guitar string is kind of oscillating this way, at least the way that I'm oriented. And so the acceleration in time, is just utt. This is the second derivative of u with respect to time. The first derivative is velocity, the second derivative is acceleration, in that vertical displacement direction. So mass times acceleration is rho delta x utt. Now I need to derive what my force is equal to, and I've already kind of alluded that my force is going to be from the y components of these two tensions not being equal, because the angles are not equal. And so that's what we're going to derive now. So the force in the y direction is going to be from these tensions. And I've seen this derived a number of different ways, and I kind of have my own favorite way, but there's no right or wrong way. There's lots of ways of coming up with the right answer. So what we're going to do is we're going to call this angle here theta, and we're going to call this angle, let's see if I have enough room here, theta plus delta theta. We're just going to kind of define, this angle here is theta plus delta theta, this angle is theta. And we're going to say that the force in the y direction, the force I care about, is F equals, and I'm going to define it so that this one is pulling in the kind of positive direction, this one's pulling in the negative direction, so minus t here, plus t here. So the force is equal to t, only the vertical component, so sine of theta plus delta theta, minus t times sine of theta. That's the force in the y direction, okay? And I could just take this expression and say that equals rho delta x utt, and that's absolutely true. That is Newton's second law. That's conservation of momentum in this section of the string. But this expression here is not that useful. I want something that's uxx, not something in terms of theta. So how do I get this uxx from this expression here? And the way that I do that is, again, using the small angle approximation. Cosine of theta, well, so sine of theta is just theta. Sine of theta plus delta theta is just theta plus delta theta. And cosine of both of these are approximately equal to 1. So if I divided both of these by cosine of those angles, that would be basically dividing them by 1. And so because of this small deflections, this small angle approximation, we can essentially say that this is approximately equal to t. And now instead of sines, I can just replace these with tangents. Same deal, doesn't change anything. So tan theta plus delta theta, that's a delta, sorry, minus tan of theta. Okay, so again, just from the small angle approximation, this force is now my tension times tan of this angle minus tan of this angle. But the kind of cool thing is, and I think I picked this up, watching another lecture online, and I hadn't realized this since, I guess I was a high school student probably, like it's something you learn and then at least I forgot it, is that tan of theta, this is super cool, tan of theta, of course, is, the delta y over the delta x, but that delta y is u. So that's essentially partial u, partial x. So partial u, partial x is tan of theta. So this is essentially, partial u, partial x evaluated at x plus delta x at time minus partial u, partial x evaluated at x at my given time t. I'm going to say this one more time. We're saying that the force that's accelerating this piece of the string, or the vibrating string vertically, is the vertical component of this minus the vertical component of this. So t sine theta plus theta dot minus t sine theta. We can change those signs to tangents because of a small angle approximation. And now tan of theta is essentially the change of u with respect to x. Partial u, partial x. Partial u, partial x here minus partial u, partial x here times tension is the force in that the force in that string. And so now what we're going to do is we're going to take this expression for force and this expression for mass times acceleration and set them equal to each other. So I'll do that now. So I have, and I'm going to divide both sides by rho delta x. So I'm going to get u tt equals this expression divided by rho delta x. So t over rho delta x times, sorry, this is a squeaky marker, I know it drives some people crazy, partial u, partial x, evaluated x plus delta x at time t, minus partial u, partial x at x and t. And now, of course, what we're going to do is we're going to take the limit as delta x goes to 0, right? We always were assuming that this was going to be an infinitesimal little section of string, like a guitar string. And so now what we're going to do is we're going to take the limit as delta x goes to 0. And the limit as delta x goes to 0 of this expression divided by delta x is just the derivative of partial u, partial x with respect to x, which is the second partial derivative of u with respect to x. So I'm just going to write this out. This is, maybe I'll write it in pink. And so now what we're going to do is we're going to take the limit as delta x goes to 0 of t over rho, 1 over delta x, partial u, partial x, x plus delta x at time t minus partial u, partial x, x in time. And so the limit as delta x goes to 0 of this expression here is just the derivative of this quantity of partial u, partial x. So that's partial squared u, partial x squared. So this thing here is just u sub xx, which we're defining as partial squared u, partial x squared. And so now what we have derived the wave equation. We're at the end where utt, the second partial derivative of u with respect to time, this is the kind of acceleration term, is equal to t over rho times uxx. So this is the wave equation where c squared equals t over rho. Okay, the tension divided by the linear density. So this is really cool. Maybe I'll just do like a super quick recap of how I derived this in a little bit. But I want to point out that this was essentially very intuitive. So now what we have is we have this wave equation where the wave speed itself, c squared, the square of the wave speed is directly related to the material properties of that guitar string, the tension in the string, and the linear density. Okay, so we'll revisit this in a little bit. And in the next lecture, of course, what I'm going to do is we're going to actually now solve this equation for given boundary conditions. So I'm going to take, again, we're going to take the guitar string pinned between x equals 0 and x equals L. That's kind of the length of the guitar string. We're going to pin it. We're going to tension it up, so that we have some tension. And we're actually going to solve this wave equation using the separation of variables. Very, very powerful method in partial differential equations. My last video I just put out was all about separation of variables for partial differential equations for Laplace's equation for the heat equation. Now we're going to do it for this wave equation, okay, which is arguably even more ubiquitous, right? The wave equation is everywhere, from optics to guitar strings to acoustics, right? Let's say I'm on my slack line and I'm whistling. The acoustic waves generated by that are also governed by this extremely important wave equation, a second order hyperbolic partial differential equation. I'll tell you what I mean by hyperbolic in a little bit. This is not just hyperbole. Okay, good. So the quick recap of how we solved or how we derived this wave equation from scratch was that we basically zoomed into a little infinitesimal segment of our guitar string. So this is the guitar string here. It's a little tiny segment, from x to x plus delta x. We made some fairly simple assumptions that this string is under enough tension that gravity is negligible compared to the tension. So the dominant force is from the string tension. We made the assumption that the deflections are relatively small, again, so that you can use kind of a small angle, small theta approximation. Even though I drew this with a really exaggerated theta just to make it easy to draw, if you look at your guitar string, it's really not moving a lot compared to the length L. And so these deflections are small. And those small deflections allow us to make the further assumption that the tension is relatively constant throughout the string. So the tension, at the end that you twist, the little thumb screw to increase the tension, that sets the tension at a constant level throughout that entire guitar string, even when the string is moving. So given those assumptions, you can essentially write down force equals mass times acceleration, F equals ma, on this segment. And then by keeping careful track of what all the forces are and what all the accelerations and masses are, you can derive this wave equation. Okay, so remember, F equals ma is just conservation of momentum, in this case, vertical momentum of a little mass of guitar string. So the mass is rho delta x, because rho is the linear density. So that linear density times delta x gives you the total mass in that segment. The acceleration of that segment in the vertical direction is utt, the second derivative of u with respect to time, because u is its vertical position. And so mass times acceleration is kind of the easy part to derive. The force, it's not really that much harder. You take the tension force, which are always tangential. I guess that's another assumption I should have made. That's kind of an obvious one, is that the tension is always tangent to the curvature of that string. And so basically, the fact that the string is bending throughout this little delta x segment means that the vertical component of my force on the left side is not exactly equal to the vertical component of the force on my right side, and there is some net vertical force accelerating this little bit of string up and down. That little net vertical bit of force is given by t sine of theta plus theta delta theta minus t sine theta, the vertical force on the right-hand side minus the vertical force on the left-hand side. Okay, we're also, of course, assuming because of this small angle approximation that the cosine components, the kind of x components of these two forces, are very, very nearly equal to each other and equal to 1, because cosine of a small angle equals cosine of this other small angle equals 1. We assume that there is kind of no net force moving this thing in the x direction, just in the y direction. Okay, so our small angle approximation then goes into this tangent. You can basically turn these signs into tangents because, again, dividing by cosine doesn't do anything for small angles. And then we use this kind of neat little trick that tan of theta is equal to partial u partial x. It's literally, you know, whatever delta in the vertical direction, which is my u variable, delta u, delta x. And if I take that limit, I get partial u partial x. And so now when I combine this force with this mass times acceleration into one equation, and I take the limit as my delta x goes to 0, I recover that this force component here has to equal uxx. My force is proportional to the second derivative of u with respect to x, which is another way of saying the curvature of the string in kind of with respect to that x variable. This is the curvature of the string. So higher curvatures, kind of a sharper bend, is going to be a much bigger force that's going to accelerate my string. That makes sense because my string doesn't want to be really, you know, tightly bent around a very, very sharp point of curvature. Okay, and that's how we derived this equation. So last thing I'm going to do in this lecture, you know, in the next lecture we're going to solve this thing with separation of variables. Last thing I'm going to do in this lecture is revisit the guitar string. And so I want to think about if it makes physical sense that, you know, how the tension changes things and how the linear density changes things. So what I would expect is that increasing the tension T should increase the speed, the wave speed C. So if I take my low E and I increase the tension, am I on the wrong one? I'm on the wrong string. Okay, now you can hear it. I'm increasing the tension. You can hear it's increasing that wave speed. Now I haven't directly shown you, this is something I'll show you in the next lecture when we solve this using separation of variables. Remember, when this string vibrates, the string itself is governed by the wave equation, but it's also oscillating the air and creating these acoustic waves, which are also governed by the wave equation. And so kind of as, you know, as the speed of information travels through this guitar string, what I'm going to show you is that kind of the vibrational frequency also depends on this C quantity here. It also depends on the length, which is why having a longer string would make this a lower frequency and having a shorter string would make it a higher frequency. Okay, good. So increasing the tension makes it a higher pitch. Decreasing the tension makes it a lower pitch, a lower wave speed. Okay, now let's talk about the linear density. So the linear density is literally, you know, how much mass there is per unit length of string. So my thicker strings have a higher linear density, a larger linear density than my smaller string. Just literally because it has a smaller cross-sectional, the smaller string has a small cross-sectional area. It weighs less per centimeter than my larger string. And so what that means is that my larger string has a big rho, and so dividing by a big number makes C lower. So my big string has a lower wave speed than my small string, assuming that they're made of the same material. You know, let's say they're both made of metal, the same metal. Now another way that you can change this, and that's actually how these strings are, is that the three lower strings are made out of metal and the three higher strings are made out of nylon. And so the nylon also has a lower linear density. So that's another way to make this number smaller, the lower linear density for those higher strings, which makes them, you know, higher pitch, higher wave speed, but without making them teeny tiny. So if you want your strings to be, you know, just the same thickness but still be higher pitched, you can make them out of a lighter material like nylon. Okay, so these are all kind of cool outfalls directly of the F equals ma physics that went into deriving this wave equation for this vibrating guitar string. Okay, so in the next lecture, we're going to solve this thing using separation of variables. We're going to still look at how that guitar string vibrates. We're going to look at how the sound will change as we change things like the length of that guitar string, these material properties. I'm going to revisit this once we actually look at the solution of this wave equation. And we're going to do that using separation of variables. This is probably, for me, one of my favorite new lectures, because it took me, a long time to feel comfortable with this derivation and the solution. But now that I do, it really is kind of a piece of cake. Okay, so I hope you find this as interesting and as fun and as widely applicable as I do. All right, stay tuned. Thanks.